Peter too. No problems. My name is Peter Heusinger, and I manage the group here, Distributed Systems and Security. And I talk a little bit more about the topic energy efficient virtualization and orchestration. So I think everybody from your side knows data centers with big servers, and in this scenario, a typical virtualization and orchestration is used. And we have analyzed the possibility to transfer this technology into the part embedded systems. But Peter one has talked about really small embedded systems with a microcontroller, often without an operating system. We talk here in an area of embedded systems at the performance class of a Raspberry Pi. But typical use case are automotive, automation, or radio access networks in big mobile networks. And our target was to analyze it is possible to save energy with virtualization in such embedded systems. And you see the typical situation here. We have 3 embedded systems, at example Raspberry Pis, and on every system there's running a container which only needs 30% of performance and resources of this system. I know this is not the typical situation. Every engineer will have a situation that the processor is optimum used as possible, but in part load scenarios, there can be the situation that really only a part of this embedded systems, of the performance of this embedded systems is used. And now we have analyzed it is possible to compact all the 3 containers into one system. Okay, we need a little bit reserve for performance, for if the system actually, yes, needs more performance, and to switch off the 2 other systems. So we have the same functionality in this system like in this system, but in this system we only need one, or we run only one processor system, and all the others are shut off. This is the basic principle of our technology, of our idea. And the first step was to analyze how much performance such a embedded system needs. So with a very precise voltage meter, we have analyzed the power consumption of a Raspberry Pi, at example, from 0 performance. So 0 performance don't say that the system is shut down. It says only that you have 0 performance for your use case. And we have the full power where completely 4 cores in our ARM processor are running under complete or under full performance. Then we have the most significant performance here, or the most significant power consumption. And it's very interesting that this is a good line. It's very homogeneous. And 3 points are very interesting. The first point is that I have no performance, 0 performance for my use case. I need 4.4 watts. Yes, absolutely without sense, I say. And under the full power mode, I have a power consumption of approximately 6.5 watts. Very interesting is also that the difference between no performance and full performance is only approximately 2 watts. And now we have analyzed, here's also a system with 2 embedded devices, both from the type Raspberry Pi. And all the 2 are running with a performance of 50%. And we have analyzed how many power this situation consumes and how many the situation consumes if I compact the 2 applications in one Raspberry Pi and shut down the other. And you see, here we have altogether approximately 11 watts, and here we have only 1 watt more than one consumes in 50% performance. And so I think it's clear that if it is possible to have such a situation, it's possible to save energy. Okay, the main topic is that if you have a system which is always running complete with 100%, I can use this energy savings mechanism. But in the real life, we have always situations where we have the so-called part load. An example, there are some results coming from a project called Edge Limit. It was focusing on radio access networks for 5G. And I think in a 5G mobile network, it's typical that you have time where you need the full performance of a mobile network, at example, and there's time where you have not such much performance. At example, in the area of a stadium, you have a football play, and if the football play is going, you have many, many visitors, and perhaps they need the mobile handies, then you need 100% performance. But if the game is over and all visitors are gone, I think stadiums are often outside of the city, at example, then you can switch parts off. And this is the basic mechanism here. If you can switch off parts, then you can use the distribution method to save energy. And on this project, we have analyzed in the radio access networks different parts. So first, we have the so-called radio unit. Radio unit is the part which makes a physical layer, which sends your information to the air interface. And then, at example, you have antennas, and every antenna element has an amplifier. And in this project, the technology of this amplifier was optimized. And you see in the 5G area, one antenna element has many, many single antenna elements. So we have a scaling factor. If we optimize an amplifier with 1% more energy efficiency, so it explodes in the altogether efficiency. On the other side, we have optimized some parts in the signal processing. And here on the left side, we have a processing unit. And this processing unit is also using a processor we use or in the Raspberry Pi is used. And this is the method where we have analyzed it is possible to optimize in a 5G radio access network with shifting informations between a server in the radio access network and on the processors, many processors, on the radio unit sides. Why many? Because this part is only a third of the complete radio unit. An antenna segment covers only 120 grade of angle. So we need 3 antenna segments to cover all 360 overview. And on the other side, we have many radio units. And so I come to my last slide. Here we have the overview of such a radio access networks. So we have a server, which is also responsible for signal processing, for physical layer processing, and we have the different radio units. And in a high performance mode or in a full load mode, I need all radio units. But if I go back to the stadium scenario, after the game, I can switch off, at example, 1 of this or 2 of the 3 radio units. And so I can use the computing resources, not the physical layer or not the power amplifier. I switch off the power part, but I can use the computing part, and it should be possible to shift program parts of the distributed unit into the switched off computing resources of the switched off radio units, and then I have the possibility in the optimum to shut down the server. And this is a method where we have analyzed how much energy I can save in such a situation. Before we can do this, we had analyzed it is possible to create a part load scenario in a 5G network. And here on the upper figure, you see a typical 5G radio unit situation, at example, in an industry hall, in an automation area, and the red crosses are typical, the radio units, and the blue points are typical positions of user equipments inside the building, at example. And so we have analyzed, at example, if in the automation area we have a break, so we don't need the complete power of the network. So it's possible to switch off parts of the radio units, and we have analyzed if I switch off parts of the radio units, that do we reach enough quality of service to cover all the, the necessary user equipments inside this situation. This was the part one, and the second part was that we also analyzed how can I change the position of radio units. Because if somebody is constructing a 5G radio access network, it makes no sense to position as much or so much different radio units in the system. So we have also analyzed, are there different deployment scenarios, at example, only 4 radio units in the edges of the hall, or only on the upper or the lower side, or here mixed, and then we have analyzed the quality of service. At the end, we had analyzed 3 load levels over 24 hours, where we met all the information or all the necessary performance in these levels, and then we have analyzed, is the quality of service good enough if we switched off parts of this radio access networks. Well, this first from my side. I talk a little bit more about tomorrow, and we will work on this side in a use case in the workshops in the next days. So thank you. Questions? If not, yes?
Does it take a lot of energy to turn on and off the specific servers or stations?
No, the turning on off is no problem. More problem is today that if you are running, we have here a link hall, it's called a hall with 2 5G campus networks here in this location. And our problem actual is that the server in such a system is always running with full performance or with full power. And the reason for this is that in an industrial environment, you use low latency. And if I go in a low latency scenario into any energy optimization modes, then I need time to drive up the system. And this is the reason that all the companies which are integrating such a system with servers inside a campus network always switch off all energy savings methods. It's completely contra energy saving to run a 5G campus networks. In the area of outside, in a public mobile networks, we have another situation. Then, because energy is very consuming, money consuming, it's really so that the provider shut off parts of the system, but they have also problems in the project I've shown here. We had the Deutsche Telekom inside the project team, and they had said they have the problem that the method to shut down the power or the possibilities are too few. They need more possibilities. And it's not energy consuming, but it's time consuming to switch on or switch off such a network. Yes?
As a result, which of these 3 different deployment layout was most successful?
I don't understand.
As a result, which of these 3 deployment layout was successful? I mean, was most successful?
We have such a situation. We have here inside our house we are searching on positioning technologies. Positioning needs that you can find the position of a user equipment of a human person or a transport system. And in many cases, one radio units would be enough to realize the data communication or to realize the audio communication. But with one component, you have no possibility to locate somebody. For locating, you need a minimum of 3 radio units. And so the typical scenarios here are good enough, but it's a question of the area inside. If you have a smaller area, it could be enough to go into the edges. But if you have a higher area, if you have a big hall, then you need, at example, only the scenario here in the middle of the 3 diagrams.
So it depends.
Yes.
That's
Always, how always in the life, it depends.
All right, thank you.
Sometimes communication takes longer time, so better you can compute without communication. So do you also consider that scenario in the simulation?
We have analyzed the problem because in all distributed systems you have the problem of the communication. If you have a container or 2 containers in one computer, you have no distance between. You can communicate in a very fast manner. We have analyzed this, and in such systems we have the possibility that you have always a big data transfer, because in the physical layer you transfer data with over 1 or 10 gigabits per second. So the little bit communication between 2 components which have a distance of 1 or 2 or 10 meters, there you have no problems. But communication also has an energy consumption. And you have to look where is my problem? Is the problem, or is the energy savings bigger if I have all inside my node, or if I have to communicate? But an interesting result of our research was that the communication of such systems, the additional communication part for the situation that 2 containers communicate each other, has only a little bit more energy. If you need an additional communication, at example, then you have another situation. But in a typical communication situation, the additional part amount is not very big. Okay, no more questions. So thank you for your interest, and I hope I can give you some more information tomorrow.